going to talk about is linear programming, and in particular, learning how to do sensitivity analysis. So towards the end of this presentation, if we get to it, we'll talk about how to look at a particular solution, and we'll see how by changing one or two things or asking questions about what would happen if we change this one thing, we'll see how that will change our solutions, if it changes our solutions. And we'll also see how it changes our objective function numbers. So the main thing that we want to do here is make sure that we know whenever we're doing sensitivity analysis to understand for the optimum solution that we come up with, for what range of values, whether that be our objective function coefficients or whether it is our constraints, what range of values will that same solution be valid for. And as we do our what if analysis on our situation, there will be some questions we'll be able to answer, some that we will not be able to answer because of that. So that's basically what we're trying to work toward. During the beginning of the presentation, we will go over different scenarios and situations that will show us if we do this one thing, how it changes our feasibility region, or how it changes, or how it changes our constraint equation as far as how it looks graphically. So we'll start off there and eventually move into sensitivity analysis. All right, so let's get started. So of course, first thing we want to do is understand using graphs the impact of changes of the objective function coefficients, right-hand side values, and constraint coefficients on the optimal solution of a linear programming problem. And then, of course, we want to generate the answer in sensitivity reports using the Excel software. If you've been watching my other two videos, you already know that we know how to do this. It's just a matter of selecting those reports and actually seeing them. We also want to interpret all parameters of these reports for maximization and minimization problems. And then we'll talk about the 100% rule as far as if we make simultaneous changes, we can see based on what we change, what is the maximum amount of change we can have and still have the same solutions. Okay. And then we'll see the impact of putting a new variable into a situation to price out something. All right, so the reason why we use sensitivity analysis is because, of course, in the real world, we have situations where we just can't accept one solution for that one situation. We have to be a bit flexible on that. Okay? We also know that, of course, values change, and with most managers, you're wanting to know, all right, well, if I can achieve this, how many different ways can I achieve it? Because if you just count on one way of let's say, making profit or revenue or whatnot, when that doesn't work, what do you do then? So you actually have to be proactive and plan for that. So that's where what if analysis comes into play. And so, as I've mentioned before, sensitivity analysis helps us to be able to answer the what if questions without us necessarily having to change our model to do it. And we can sort of ask questions about, all right, well, if we change our objective function, change one of our constraints this way, how would that actually affect our solution? And so we're coming back here to the flare furniture example. And again, we've seen this before, so I'm not going to go through all the details here. But the purpose of why I want to go through this now is because what we want to do now is actually understand in detail what is happening to the feasibility region once we change stuff. Okay? I'm also going to go in detail some as far as when we change these, coefficients or constraint coefficients, how that's actually changing our lines in this case that go along with defining what our feasibility region is. All right, so you notice here I have this written here, and I have this because I want us to sort of understand really what is going on as far as how this looks and how do we actually plot these lines. So here we know that at 3t plus 4c, excuse me, the 3t plus 4c is less than 2400. We know there that is a particular, we know that this is a particular constraint, and of course there's an associated equation with that. So we want to look at how we can actually plot this, plot this, plot this, plot this. And let's just start off here. Now we know if we wanted to come up with our profit coefficient, or I should say objective function here with our coefficients, we know that when we talk about a line in standard form, kind of like how this is, we know the slope of that line is going to be minus a over b. And just to bring this back to remembrance, we know that because if I take this equation here and solve for y, the first thing that I need to do is subtract both sides by ax. And that cancels to 0. I end up having b times y equals minus ax plus c. And I divide both sides by b. When I get that, I end up getting this. Now, the point here is that we know that this is the same thing as the slope whenever we talk about the slope-intercept. And we know that this is the same thing as the y-intercept when we talk about the slope-intercept of the equation of the line. So that's where I'm getting the slope is equal to minus a over b. And of course, that's going to tell us a lot about how to actually draw this particular line. Okay. So I'll go ahead and erase all this now that we know that. All right, so here for this particular objective function here, we know that our slope is going to be minus 7 over 5, okay, which is about minus 1.4. So we know that our objective function associated line is going to look something like this. For our other constraints, here we'll see that we can actually get this, plot these 2 points here. We're going to find the x and y intercepts. And so if I allow, I shouldn't really say x and y here. This should be more t and c. So I'm going to change it to that. So it kind of goes along with what we're doing. So t we're treating like the x, and c we're treating like the y. And so here, t is equal to 0, then of course this entire term goes away, and all you have is 4c plus, 4c equals 2400. Let's get this out here. Of course, if you divide both sides by 4, then you'll end up getting 600 here. So t is 0, 6 is 600, and We also know do the same thing when c equals 0. Then, of course, 4c goes away. We just have 3t equals 24. And of course, if we divide both sides by 3 here, that ends up being 8. So, our point here is that we know that this particular line for the carpentry constraint is going to consist of a line that goes through these 2 points. And of course, the slope will be minus the a, which is 3, divided by b, which is the 4. So we know we have a line that's going to be negative, and it's going to go through these 2 points. All right, so if we do a similar thing with this next constraint here about the painting hours, then we know for the t axis here, if we let c equals 0, then 2t equals 1,000, which means t would be 500. And of course, if we let t equals 0, then this first term goes away. And all we have left is c is equal to 1,000. And of course, our slope for that one will be minus 2 over the understood 1, which is just a negative 2. Now, c equals 450. Of course, this is in place of y, so this is just looking at this like it's y equals 450. This will be a horizontal line, so it'll go like this. And that's going to sort of top out our feasibility region. So I'm just going to make this a little smaller so we can fit the rest of the movement. Then I'll just have to scroll. Let's get this back to you now. Let's get back to where we were. All right, so now all I want to do is go down some so you can get the rest of these. So these. So now once that's done, of course our t equals 0. T is acting like the x variable. So because of that, we're treating this like x equals 100. And of course that is a vertical. We know that because x equals 100 says every point that's on this line has to have the same x coordinate. Okay? So you can have point 100, 0, 101, 102, 103. I like what I'm saying here, 100, 0, 100, 1, 100, 2. And of course that's going to sort of be our variable on the left side of our feasibility region. These two together, the t equals 0 and c equals 0, are acting like the lines x equals 0, which is vertical, and y equals 0, which is horizontal as well. And what these two things basically do is keep us in the first quadrant. And of course, if we were talking about quadrants here, we go counterclockwise to talk about them. The t equals 0 will keep us this way. The t equals 0. Remember, t is acting like the x, so it will keep us here. And the c equals 0. That's acting like y equals 0, which is horizontal, it's keeping us there. And of course, we know that from our constraints here that we're actually saying that this is greater than or equal to and greater than or equal to. So what that means for us here is that we are going to be on the right side of t equals 0, and we're going to be on the upside of c equals 0. And of course, when we look here, we see that the intersection of all that is essentially quadrant here. So if we put all that information together here, then we see that this is what our graph ends up looking at. Okay? And so you see how we have the objective function, and we've actually labeled a certain profit on that. So we want to choose a different color here. Let's choose black. Here for the objective function, we see that this is the line, and of course, if we made the profit more, then this line would go further out this way. Okay? Now, you see that when we say the level profit line, the level profit line, which is in blue here, is a line that, of course, still negative, has the same slope, but it also intersects the feasibility region in a place where you get the maximum profit. Okay? So part of what we do whenever we run the Excel solver is to try to figure this out. Or if we were in Unit 1, we would do this by hand by using our corner points. Okay? Now you see the other constraints here, the painting constraint, which is this line here. You see how that goes through the point 4 right here. And that also keeps on going down like that. We have our maximum tables constraint there. And that was the T, I believe that was, let's go back, because I forgot whether that was less than. Yeah, T is at least 100. Okay. That's what I was thinking. So that is that particular line here. We also see that maximum number of chairs allowed, and actually this should be minimum. Now I think about it, because greater than or equal to 0 says you have to at least have this one. So we come back here, this should be minimum number of chairs now. Let's see. All right. And, maximum number of chairs allowed. We see that, I believe that was the C equals 450, I believe, right? Or C is less than or equal to 450. So here we said that was a horizontal line. And we also have our carpentry time constraint, which is here. Okay. And if we go back page there, this was the carpentry time constraint. Our 2 points here was 0, 600, and 800, 0. So those are y and x intercepts respectively. And you can see here that here's the point 0, 600 for the carpentry constraint, and here would be that point 800, 0. So in short, this is how all this stuff will look once we actually were to draw. Now, I know it looks very confusing, and I know it's a lot going on and a lot to keep up with. And so that's one of the reasons why we actually use the Excel solver to help us out, because we can actually do everything algebraically in there without us necessarily having to look at the picture and the feasibility region looks like itself. Yeah. All right, so now what we're going to do is go over the types of things that we study when we're doing sensitivity analysis. So we're going to change one of these three things here. And as we change each one just on its own, we're going to see how it affects the feasibility region. In some cases, it will expand it. In some cases, it will contract it. All right, so our objective function coefficient. So let's say you want to change profit contribution for the amount of tables that we have. Okay? Now, if we were going to change this number here from 7 to 8, then that means we're increasing the amount of profit that we have on the tables. But what that also means is that our slope of the associated line is changing from negative 1.4 to negative 1.6. So that means from a negative standpoint, it is getting more steep. So if negative 1.4 looks like this, then negative 1.6 is going to rise up a little bit, will drop down, so to say. If we change this from 7 to 6, then that means that we're decreasing the profit per table by $1. So it's going to have less of a negative slope. So of course, if this is negative 1.4 and negative 1.2 would be more like that. If we changed it drastically, let's say by $4, we went from having $7 profit per table to 11. Then of course, we're going to change it a lot. And so now that associated line will look like this. But if we went down $4 in profit per table, then it's going to be almost horizontal at that point. And it look more so like this. Okay? So we want to recall again that the optimal solution is the corner point of the feasibility region that passes through a line with the same slope as the objective functions associated with it. Okay? I'll read that one more time. Recall that an optimal solution is a corner point of the feasibility region that passes through a line with the same slope as the objective functions associated with it. And so I'm going to go back there to show you, because that's exactly what this level profit line is. So this line, which is right here, has the same slope as the objective functions, and it intersects a corner point. And of course, we know for that particular corner point, we get the most profit out. So that's what that's saying. Now, as we change our objective function here, in other words, as the profit change, if we actually change these coefficients, then the way that this line is going to look on our graph is different. And of course, as we're changing the slope, sometimes we could also be changing what corner point it hits, if it hits any corner points. And sometimes we'll have instances where it hits multiple corner points. So we need to be mindful of that as well. So here again, we know that if we take a line in standard form, we know this is what the slope is. And you see how if we have these different changes to our profit function, then everything changes. So I'll do this quickly since we kind of have an idea of what's going on here. So the slope of this line is going to be negative 8/5, which is like a negative 1 3/5, which is the negative 1.6. So that's how we get those slopes. For this one, of course, we went down $1. So this one we started at 7, we went up $1. Then we started at 7, went down $1. So now this is a negative 6/5, which is negative 1 1/5, and 1/5 is just 0.2. So that's where the negative 1.2 comes from, I was talking about earlier. If we go from 7 up to $11, then the slope is now negative 11/5, which which is likely to -2 and 1/5, which is a -2.2 because 1/5 on its own is just 0.2. So that's how we get that slope. Go down some. This last one. And so here for this last one, we'll do the same thing. Slope is -3/5, which if we divide that, we just get 0.6. So this is where I actually get all of those slopes from. All right. So now this is what happens if we go from having our level line here. So this is the one whenever we are going down $1, and this is the one when we go up $1. So the red is when we go up $1 on the profit for the tables, and blue is when we go down. You see in these instances, because the change is relatively small, we still have the same solution. Okay? So you see that a change of only going $1 up or going $1 down in profit doesn't really change the optimum solution that much. So that is what this is trying to show. Now, notice that when we go up $4 or we go down $4, notice that we don't hit this corner point at 4 anymore. We don't hit that. And so now we see that if we went down $4, then the optimal solution now is this point, 0.3. And we also see that if we went up $4, then the optimal solution now is here at t equals 500, c equals 0. So effectively what this is saying is that, and we'll take the case of going down $4. So if we go down $4 in profit in the table, then what we're effectively saying here is that we need to make less tables and more chairs in order to achieve maximum profit. In the case of if we change our profit on tables to go up $4, then essentially what this says here is that we need to make all tables and forget about making chairs at that point. So we can get that much profit from each table. Okay? And so by being able to draw these lines and understand where they hit as far as the corner points are concerned, that lets you know something about your particular situation here with limits. Now, the main thing that we want to illuminate here is that the $4 change, whether we go up $4 or down $4, is such that it changes what our solution is going to be. And so it's outside of the range that we can change the profit levels for the table in order to stay with the same solution. So that's part of what our sensitivity analysis report lets us know without us having to draw these graphs. It lets us know how much can we change the profit for the table going up or going down and still have that same original corner point solution of 4. All right, so we saw that the impact changes here to our objective function coefficient. It really just depends upon how much we go up. And you see that different solutions are found whenever that change is too much. So now what we're about to do is look at our right-hand side values for our constraints. So to be clear, this was our carpentry constraint here. So we're trying to see, hey, well, what happens whenever we change this number here? Okay? And we're going to look at it in, let's see, for the painting, and this is what we have. So we're going to change these numbers here on the right side and see how does that affect what's going on. So in short, what we're going to see is that it changes our feasibility region. It's either going to expand it or contract it. In other words, make it bigger or make it smaller. And we know that the constraint is also a binding constraint as well. So the shape of our feasibility region will change. All right. So looking here, we see that we have our objective function here, and we're just assuming a profit of 2,800 right there. But now we see that this was the original constraint, and I'm going to do this in green. This particular line, turn out well. Try that again. This particular line right here, that line right there is the original painting time constraint. Okay? But what happens is that we basically say, hey, I can increase the amount of hours from 1,000 hours of painting I can pay for my workers to 1,300. Then that line now switches, and now it looks like this. So I'm going to draw that. So this is what it was in the beginning. This is what it is when it finishes. And so now we see, because of that line, well, because of the right-hand side changing from 1,000 to 1,300, we see that our feasibility region has been expanded. Okay? So the binding constraint on the right side has expanded the feasibility region. But also because of that, what we've done is we've changed the solution. Okay? We also see that here, 4A, this point here is also a solution. And so essentially what this is communicating to us is this. If we have more hours to do painting, then that means we should make more tables and less chairs. Okay? So that's by expanding that feasibility region, that's what's happening. We also see that from our optimal level line, profit line now, of course, this line has the same slope as this one. Okay? But it goes through the corner point here that gives us the largest profit, and we see that the profit has gone up. If you remember from before, our profit, when we had our original solution, was $4,040. But we see that if we can afford more painting hours, we can also get more profit out of it. Okay? It looks like we're experiencing almost, it's like $780 profit. Okay, so that's how the binding constraints, or if we change our right-hand side constraint and increase it, what happens is our feasibility increases. Now, we see that, of course, if we reduce the hours from 1,000 to 900, our feasibility region decreases. So originally, I'll do this again. Oh, sorry, that's the wrong. We're going to do that first. So I'll do this in different colors. We'll start off with red. And so this will be the original constraint line again. So this is the, I think for this one, 2t plus c is less than 1,000. And then with the 900, switch that. That is this one here. And of course, you see the little gap that's in between there. That's the feasibility region change. it is less now. The area is less. And so so here we see that 4B now is our actual optimum solution. In this case, whenever we change that. So we see here that if we decrease the amount of painting time, what actually happens here is that we need to make more chairs and less tables. Okay? So, of course, with this particular constraint, painting time, the more we have, the more tables we need. The less we have, the more chairs we need. And that's pretty much what that's trying to communicate to us. All right. So we're going to talk about shadow pricing now. And shadow price is a change in the optimum objective function's value for 1 unit change in the right-hand side value of the constraint. And it only applies over the range. So let's move on. Give me a second. I'm going to set some other stuff up. Get started. All right. Okay. So anyway. For shadow pricing, I guess another way to think about this is if we're talking about a situation where, let's say, we change. Let's take the hours, the painting hours again. That would be a good way to sort of think about this. Okay. So remember, we originally had 1,000 hours. If we wanted to change the amount of hours from 1,000 hours to 1,001 hours, then we're saying the shadow price will let us know how much actual profit we would receive by changing just this constraint by 1 hour. Okay? And so let's say, just hypothetically speaking here, if we change this by 1 hour, then our profit will go up by 90 cents. So our shadow price here would be 90 cents per hour change. It would also work the other way. So if I wanted to go down 1 hour to 999, then it means instead of adding adding 90 cents to profit, I would take away 90 cents from profit. And so my point in this is that the shadow pricing, or shadow price rather, helps us to be able to see what's going on as far as how profit is changing without us having to come up with a whole other line to do. And so that's one of the things that the Excel solver, when you do a sensitivity report, actually helps out. Okay? So we'll look here in these cases of painting time being drastically changed from 1,000 to 1,700, and then relatively drastically changed from 1,000 to 700. So, of course, in this case here, we're expecting the feasibility region to increase a lot. We're expecting the feasibility region here to decrease a lot. So, if we look here, you see how this is the original objective function that we're talking about with standard profit here of 2,800. This particular line here, again, that is our painting hours constraint line, the original one. Okay. The red line is what happens when we change it from 1,000, which is here, to 1,700 hours. And so you see that that line is so far out that it doesn't even intersect the feasibility region. And so in this case, we call that constraint as redundant. And basically what that means is that we have so many painting hours that it doesn't really affect anything. Okay? We have enough painting hours to do whatever it is that we want. Okay? Now, what the painting hours, what that increase does affect, however, is our solution, our optimal solution. And so this line right here is our revised level profit line, meaning now that our feasibility region has expanded, because we expanded it from $1,000 to $1,700, then the only place where our objective function load line, level line is going to intersect is right here. I'll do that in a different color just so that we can see that. It's going to intersect right here at 800. So again, what this means is that if we have all the painting hours that we need available to us, and 1,700 is enough for our given situation, then we basically need to make all tables and their chairs. If we go the other way, now we see that, again, this is our original painting hours constraint. And we have here, if we decrease that, I'm going to do this in green. If we now decrease that by 300 hours, so if we take this and go this way with it, now we end up having this line. Now that drastically reduces our feasibility region, and now the level profit line that we see here, which is in red, now we see it's crossing at 380. And so this tells us that we need to drastically reduce the amount of tables that we need to make and increase the amount of chairs that we need. All right. And so now we'll look at some right-hand side values for non-binding constraints here. And we're going to introduce what's called slack or surplus here. And so what we're talking about in these cases is, remember that for, I'm just going to change colors here, that for our tables, we needed to make a minimum of 100, and for our chairs, we needed to make no more than 450. So here what we're saying in terms of chairs, if we're allowed to make an infinite amount of chairs, instead of just maxing out at 450, how would that look? And if we were able to decrease the amount of chairs from 450 to 360, how that would look? And so if we look at this, everything else staying the same except for that, we see that this is the C equals 450 line here, this one, and this is the C equals 360 line there. And of course, our optimum level profit line originally goes to 0.4 right here. And so you'll see that because this point is right here, what we have right here is what we call a slack, meaning that if we produced 450 chairs, well, maxed out at 450 chairs, we would have about 90 chairs slack. In other words, 90 extra chairs. We could reduce that constraint and go up and go down to just 360, and we'll still be fine as far as our optimum solution is concerned. Okay, so that is what slack looks like whenever we draw it here on our graph to try to show feasibility region. All right, so now we've seen how we change various things to our constraints or our objective function, how it affects our feasibility region. So what we want to get into now is the actual sensitivity analysis part. So of course, from last week, we know that this was our optimal solution: 320 tables, 360 chairs, and that's how much profit we got. And of course, we know how to do all of this now. The one thing that's new for us is here. So our answering sensitivity report, we just click those, and then once we click, then we see that we'll get those reports. So this is an example of the sensitivity report. Okay? And so in looking here, we want to talk about what a lot of this stuff means. So first thing that we want to talk about is these ranges. So here is our solutions. So this is the amount of tables, the amount of chairs. And the objective functions that we have here, of course, $7 profit per table, $5 profit per chair. So these two columns actually tell us, as long as we want to keep these solutions, we can go no more than $3 up in profit for the tables and no more than $3.25 down. Okay? So in other words, our range for profit on tables is going to be, on the high end is going to be 10, and on the low end, let's say 7 subtracting 3 is 4, so that'll be like $3.75. Okay? So as long as the profit, I put 100, but it's supposed to be 10. So as long as our profits are from $3.75 to $10, this 320 for the amount of tables we should make should work. Of course, here we're saying the same thing for the amount of chairs. On the high end, we just have to add $4.33 to that. So on the high end, we can have no more than $9.33 profit, and on the low end, we have to subtract $1.50, so that would end up being $3.50. So as long as the chairs stay within $3.50 profit to $9.33, then we can still keep our same solution. Now, we also see down here with our constraints, you see the shadow price. Of course, we talked about that. So here are our original constraint values. Our shadow price just tells us if we wanted to change our amount of carpentry hours, or painting hours, or the amount of chairs or tables by 1 unit, how much would that increase or decrease our profit? So for our carpentry hours, we see that the shadow price is 60 cents. So what that means here is that if I wanted to change my carpentry hours from $2,400 to $2,401, then my actual profit would go up 60 cents. If I wanted to change and go down to $2,399, then my profit would decrease by 60 cents. And this is true as long as we stay within these values here. So, of course, for the carpentry hours, I'll just say CH for that. On the high end, I can't increase any more than 225 hours. So that would be 2,625 hours on the high end. On the low end, I can't go any lower than 900 hours below 2,400. Okay? So that would be 1,500 hours here. So as long as we stay within 1,500 hours to 2,625 hours, then this shadow price here is valid. And of course, the same kind of thing you see for the painting hours. Okay? And if you notice, the painting hours, the shadow price is way more than the carpentry hours. So this tells us, excuse me. So this tells us that if we are able to change the painting hours, increase them, then our profits are going to be affected very much so. Whereas if we decrease the amount of painting hours, then our profits are going to be affected negatively more so than it is if you do the same thing with carpentry hours. So we want to try to find a way to be able to basically look at the painting hours and try to provide as much of that as possible, because we know that's going to affect our profits as much as possible. And if we have an issue where we are having to cut back, we want to cut back the painting hours the least amount, because we know that that's going to directly affect our profit the most. All right, so now we're going to look at changes on right-hand side values here. We know that in general, feasibility region changes. We know that the optimum function values change, and we have to look at the shadow prices, and we also have to worry about how much we change things, the validity range. In other words, what I just got through describing to you here. So for the shares, the validity range is from $3.50 to $9.33. And for this carpentry hour constraint, the validity range is from $1,500 to $2,625. Okay. And we see that for a non-binding constraint, there is no change in the objective function, no shadow price, and the range is fine. So I'm going to go back here and explain that. If you see here, we have no shadow price for these two. And part of the reason for that is because, if you notice, for the chairs, we had maximum of 450 that we can make, right? But we see that we only needed 360, so we have slack there. So whenever you know you have slack, and you'll know that you'll have slack because your shadow price would be 0 here. Then you know that in that case, it's not going to have a shadow price, and you got some wiggle room. So for the minimum number of tables, of course, we know that we had to have at least 100 for the tables. And of course, we met that by a long shot. So again, there's not going to be a shadow price on that, because as long as you don't go under 100, then it's not going to really affect your profits. Okay. And of course, here, whenever you see this is Excel's way of saying infinity. So that's like 1 times 10 to the third. Okay. A very, very, very large number. So, of course, on the low end here for the chairs, it's just saying that, hey, you got that 90 unit slack there. So as long as you don't go under there, you don't change it. Of course, here's the infinity again. And we also see the 220 here. We need to have at least 100 tables. So, of course, the difference in between 320 and 100 is 220. So as long as we don't go under producing 100 tables, then profits should stay the same. All right. And so now we need to talk about the reduced cost. So what the reduced cost is, another way that we can talk about reduced cost is to call it by another name, which is opportunity cost. And so what the opportunity cost is, it says, well, by us not making these particular tables, chairs, or whatnot, how much are we actually going to lose by not doing it or not investing in it? Okay. Let's see. Let me see if I have another way of showing this. Okay. I thought I had another way of showing this, but it doesn't look like I had anything, so I'll just do it. So anyway, opportunity cost, same as what we call the reduced cost. If you notice here that for this particular sensitivity report for the number of tables and chairs. Since for the number of tables and chairs we have the slack in there, there's really not going to be much of a difference with the opportunity cost. So I'm trying to go back here and we can talk a little bit more about it here. So erase this. All right, so kind of give you an idea of what reduced cost or what opportunity cost is. We're going to look at a situation where we want to have variables to where if we have, let's say, the final value for this, instead of it being 320, let's say it's 0. Okay? So when your solution turns out, they're basically saying, hey, you shouldn't make any of those tables, any of those chairs. Then what that's saying is that for you to be able to, in this case, achieve maximum profit, you're not going to be able to do that by making the tables in this case. Okay. Now, if you want to make those tables, then there's going to be a minimum cost associated, meaning there's going to be a minimum cost that you're going to have to give up in your profit to be able to produce those tables. So let's say if that particular cost was, let's say, $2. Okay? So that means if right now, if my solution was 0, 360, then it would say make no tables, make all chairs. If I wanted to make one table, then every time I make a table, I would end up actually losing $2. Okay? So this is important to know because there may be times when you actually want to lose profit in order to sustain being able to make the kind of money that you want to make off a deal. And I'll give you an example of how I've had to do this. So I used to travel a lot as a product marketing engineer, and when we used to travel to India to try to gain some market share in that particular market, our strategy was we had to basically give away some parts in order to gain business with some of the companies. Because of course they had other companies that was already there and supplying them, but we knew that our product was better, and we knew that in the long run we would be able to serve them better. So what we had to do was say, all right, we're going to basically give away these parts here. And even though it wasn't going to be maximum profit to do that, but we gave it away so that we could secure the business. And so by doing that, of course, over time, once we gain market share, then of course we can have them locked in and we can make more profits in the future. But we had to be strategic on what we gave up to make sure that wasn't going to erode our profit margins too much. Because again, off of these deals, we knew that we wanted to make at least a minimum return on investment for them. So the reduced cost helps you to be able to see how much you're going to erode your profits by producing things that's not going to exactly give you maximum profit, but at the same time, of course, you have to manage it. All right, let's move on here. So again, this says the difference between marginal contribution and marginal worth of resources consumed. So that's just a fancy way of saying what I just got to explain it to you. Okay. All right, so here we do the objective function correction. So it looks like what we have here is we have the optimum level profit line. When we went down $1, this is the optimum level profit line. When we went up $1. And of course, this is our optimal solution from before. And you see the size of the feasibility region doesn't change when that happens. But of course, the profits are different. You go down $1, profit goes down. You go up $1, of course, profit goes up. So we've already kind of seen this before. Just trying to put it all together.